Hello and welcome to our webinar on AI, Maps, and Climate Action. I am your host, Deepthi Illa, the CEO and Growth Principal at Thedas, a growth advisory firm that elevates climate tech companies and mission-driven organizations. Prior to Thedas, I spent 21 years in technology marketing and held leadership roles at Google, Salesforce, RingCentral, to name a few. Our guest speaker today is building digital technology for our planet. His name is Mikel Maron, and he is the head of product at Earth Genome. Previously, Mikel led corporate social responsibility at Mapbox, elevated open mapping in the federal government as a Presidential Innovation Fellow, and founded community mapping initiatives, notably Map Kibera through Ground Truth Initiative. He has a long association with the OpenStreetMap project, founding humanitarian OpenStreetMap team in 2005. You may have heard of a platform called Climate Trace, which measures real-time GHG emissions. You may have heard of the Amazon Mining Watch, the Global Plastic Watch, or Seed Trees, and many such tools that help us monitor change on our planet. But do you know who is behind it? Today, we're excited to learn how these impactful tools came into being from Earth Genome's head of product. So Earth Genome is a mission-driven nonprofit that translates increasingly massive Earth data into useful, accessible, and affordable analyses to enable a more sustainable use of natural resources. Their expertise lies in working with AI and Earth data. They collaborate with researchers, policymakers, builders, and communicators, and focus on water, food, emissions, forests, biodiversity, and other key environmental areas. Our guest speaker, Mikel, will discuss the unique challenges and opportunities in Earth observation, especially focused on using mapping and AI for scaling climate solutions. He will first share how they think about products and data, and then share some of the solutions they've developed, such as Climate Trace, the Amazon Mining Watch, and their newly launched Earth Index platform. Without further ado, let me hand it over to Mikel to showcase Earth Genome.
So looking at the kind of products we do, I've roughly categorized in 4 different ways, all oriented around data. That's kind of like our starting point, and then connecting that to some real action. But there's a few different kinds of products that we build. Data Explore, so there's an existing data set, not necessarily one that we built directly. It could be part of a group that built something, or something that's already in the public domain. And building tools to really like explore this data in very user-oriented, intuitive, and a beautiful way. Data outputs themselves, so this is a production of a specific data set. Data creation tools, this is Earth Index, which is an application for anyone to build their own data set without us being the ones that are doing all the machine learning modeling. And then finally, data action, and this is where orienting everything you've learned about a domain and what's needed in order to make a decision or to do implementation. Let's assemble everything in the right way in a parameterized way so that people can make the right call on where to invest or what to do. So I have a few examples of each of these. First, to talk about exploration, Climate Trace. This is an amazing project I'm really proud to be a part of, led by Al Gore and Gavin McCormick. There's a coalition of researchers, scientists, nonprofit groups. There's a dozen core members, organizations which come together. And typically each of these organizations has an expertise in understanding a particular sector of the world, whether it's mining or agriculture or power generation or oil and gas. And they all do very highly detailed scientific and engineering work ultimately to come together and produce as fine detailed emissions modeling at a facility level as possible, both location wise and in time frequency. And so this is really the most comprehensive and the most detailed database available of emissions at, I think, ultimately at a level where you can do something about it. If you know what the emissions are of an individual steel plant or a set of steel plants, you can make choices on where the best supplier is to reduce your greenhouse gas footprint in your what you're ultimately building. So our role is to do all of the production data engineering and product design and website implementation. By the way, feel free to, if there's any questions while I go, we'll have time for questions at the end, but if there's something I can clarify or something you think is important to point out, feel free to write something in the chat, and Deepti, just let me know if you think there's something that would be good to I don't mind having my flow interrupted if there's something that's worth addressing right away.
Sure, yeah, I will let you know.
Cool. So this is the whole Climate Trace Coalition. As I said, real brings together a pretty amazing group of folks under many circumstances, quite honestly, there's a lot of coalitions. There's a lot of groups that try to bring together different organizations together, and many times they get, in my experience, can get bogged down in governance issues or become more of a talking shop and sharing stuff. What's really different is like this is really oriented towards producing something together, and it works. And so I think it's a really interesting model for how to organize collective action from a number of groups. Just to step back a little bit to give you an idea of how the data generation piece works of this. Essentially, this is an example from power plants, and there's, I would say, two main things you have to do in order to do emission. Well, there's a few things, but one of the main things is you have to know where all of these things are, where are all the power plants, and also some details about how they operate, what kind of fuel they use, what kind of technology or modifications they have, and power plants. Fortunately, there are fairly good databases of this, which have been there weren't, but they were gathered together by folks like Global Energy Monitor, who do amazing research in lots of different modes to get this base data of like what is out there in terms of the power system. So once you have that, the other thing you really need to know is how active these facilities are. And it's not, a particular power generation facility is going to be, depending on demand and other factors, it's not turned on all the time. It goes on and off. So you want to be able to detect when they're operational or not. That's kind of the key activity input, combined with all of the parameters about, how efficient it is as an operating unit. And so that's where Climate Trace, the folks who work on this piece, bring in AI models to basically look at planet imagery. And we have a great arrangement with Planet to use that imagery to identify when can you see vapor or other atmospheric effects from that facility, and that then correlates from a sample of in situ measurements. So there is good information available on some plants, particularly in the U.S., at least as of today, of when these of like what the generation profile is. So you use that, and from there you can build models which can extrapolate to any location around the world. And so that's where you need to have remote sensing imagery available at high revisit and good models, and that all comes together to build emissions estimates. One thing I'll touch on in terms of building a product is, and I'm been doing map making for a long time, is that this is a really challenging cartographic and interaction problem where we have hundreds of thousands of points with several orders of magnitude of emissions that you need to that are represented on this map. That's the size of the individual circle. So you need to both show like relatively how big something is, but if we were to just scale it linearly, the power plants and the oil and gas facilities would be humongous compared to like wastewater treatment facilities. You need to use colors in a way that works together. And the other thing is there's not only points, individual points, but there's also areas. So things like rice fields or um, for deforestation are also represented on the map. But those are two things that are hard to put together in a way that they're immediately comprehensible. So there's a lot going on this map. And we've iterated a lot to like make it something that somewhat at a glance you can start to look at relative emissions. You can kind of see what an individual country is dominated by. It's not going to answer every question at this global view, but you're able to make sense of it. And I'm not going to show you all the versions of the map that we've gone through, but it's certainly not a given that if you layer hundreds of thousands of points on a map, that it's going to make any sense whatsoever. One thing we've been building for 4 years. And one thing that the coalition as a whole has learned is like what units, what filters, what views of this data are actually really actionable. One thing that emerged and was a big part of our latest release at COP last year was a primacy of urban areas of cities. And these are because there is a real effort of many urban areas to take more account for emissions that are within their area that can be attributed to that place, and to build action plans and to start to do something to reduce emissions. So cities are kind of a first class unit on the site, which is not an easy task to do when you're trying to collect those globally. And there's a lot of information, you can keep on digging. It's a lot to assemble. So here's just an individual port. Here I'm based in Santo Domingo, Dominican Republic, so this is just close by. And so just for an individual port, we have monthly emissions available, and there's details on not only greenhouse gas emissions, but also air pollution like carbon monoxide and nitrous oxide and others. So we have to pack a lot of information in here, but still make it something that balances out the purpose of this site, which is both to communicate to a wide audience that we know something that is actionable, but then also provide ultimately a pathway to people to get the data, download it, and use it in their own applications. So that's kind of there's two parts of it, both of the explorers really make people aware of what's there, but then provide that ramp to them using the data in their own site. And we make it available in lots of different ways. We could talk a lot about like API product design as well. We think a lot about that. So that's Climate Trace. Second kind of product, data output. It's where kind of creating, we as Earth Genome creating a new data set. And the example here is Amazon Mining Watch. Artisanal mining sounds very boutique, bespoke, but it's actually terrible. But what it refers to is small groups of unorganized folks going and in the forest, clearing and looking for gold. And this is often tied to organized crime, very damaging for the environment. It can be the first phase to even more deforestation. And it can happen really fast. So it's important to be able to detect these things in a timeline where they can be acted on. And they're difficult. Mining can happen fast, and we're talking about the Amazon, so cloud cover is a real issue. And so you have to do a lot of processing to get cloud-free imagery. And then you also there's a lot of drivers of deforestation, agriculture, logging, other roads. So you need to be able to distinguish there. Here's a video kind of showing progression of mining in one location. You can see it can start slow and then very quickly kind of spread to a wide area. Ben Strong on our team went and visited this site as part of some of his field visits, and you can kind of see how much impact that can have on the landscape. So what we did was first label in a map a lot of these locations by hand, and then we assembled imagery from the European Space Agency Sentinel-2 um, uh, archives, ran a magical machine learning algorithm, but there was a lot more to it. But yeah, did a lot of tuning of our machine learning to build a very, very good gold mine detector. And this is something that we've been able to refine and run again and again over multiple years. There is an explore site at amazonminingwatch.org where you can look at this, you can zoom in and out and kind of see the details. But this, more than anything, really is directing people to get at the data and then use it in other ways, whether it's analysis or taking action. And that's really been happening. The journalists, activist groups have relied on Amazon Mining Watch as an independent source of really detailed information to really advocate and mandate enforcement. And that's happened. So on the right is actually a Brazilian prosecution. The federal police used Amazon Mining Watch data as part of their investigation to prosecute this, what is, a very illegal activity. So a lot more to come with Amazon Mining Watch. This is still, we're going to quarterly data
Mikel,
and
quick
developing now. Yeah, go ahead.
follow-up question. How
Sure.
does the AI model differentiate between what is a legal mining operation but may be authorized and what is illegal? Is that level of granularity possible or?
It is. There's probably in the case of the region we're looking at, there are no. And particularly these artisanal mines, none of them are legal because so you might contrast that with a legal operation is going to be larger scale, but typically in these areas are also like most of the protected areas, indigenous territories. And so while it covers all of the Amazon, the particular areas that are focused on are these ones where no mining activity should be happening at all. But in general, yeah, you can detect the difference because of like the scale, the location, and the machine learning model would detect some difference. But in this case, it's not something that comes up. There's really not examples of legal mining in these areas.
Got it. Thank you.
So data creation, what if we started with the question, what if anyone could make their own Amazon mining watch? Um, uh, the way that we built Amazon Mining Watch and other projects like Global Plastic Watch is we assembled all that satellite imagery. We trained a custom model, which was good at just detecting that one individual problem, and then produced a data set. If you want to do that for another kind of feature, or even the same kind of thing in a different location, you're going to probably have to start from scratch. And so for several years now, what we have been researching, exploring, building, and developing is utilizing foundation models, which is kind of similar to ChatGPT, which is a model which is trained on every available text that it can get its hands on. Foundation models for satellite imagery are trained on a large corpus of satellite imagery, not to accomplish any specific purpose, but just to kind of understand the typical structures of what is seen in satellite imagery. That model then can be fine-tuned rather quickly to determine, for any specific outcome. So there's, just like with ChatGPT, you can add additional context with your question, and then it will reply based off of what it's learned about language as a whole. So there's a number of work happening on remote sensing geospatial foundation models. We use a lot of the products developed by a lab at the Technical University of Munich, which have done really well. And there's lots of applications, and particularly what we do with it in Earth Index is do geospatial search, as well as change detection. But there's other kinds of operations you can do as well. This animation kind of illustrates the concept of what we're working with. So that was the state of Alabama, and that transformation into this kind of clusters is after you process an image through this foundation model, certain images which have kind of like similar structural characteristics are closer together in space. And what you here you can see here's a lot of chicken CAFOs, and it'll run again. So it's kind of just segmented Alabama into different clusters of what it understands is in that picture. Here to start, I think it starts with sort of mining operations, and then there's some examples of airstrips. And we rely on this clustering in the search on the back end. So basically, you give a few examples of things that you want to find, and then it finds things what are the things which are closest by those set of labels that you've added. And that's the idea behind Earth Index. And what we want to do is do all this processing of imagery and run the machine learning model upfront, so that that's not a requirement for anyone to invest that resource or have that technical understanding. You don't have to have a knowledge and depth of what's happening with the geospatial data or machine learning. What's most important is to have like a problem and an understanding of the landscape you want to examine, and then in an interactive application, very quickly you can start to build data sets. So this is a quick video. It shows the process of creating a new project in Earth Index, give it a name. We're going to search for solar installations in Cambodia. Here it's selecting a region to search at. We haven't yet, we're in the process of indexing globally, but here in this demo, you select a specific area that's already been indexed. You go into the interactive map, you find a few examples of what you're looking for. Here are the solar farms. Add a few labels, not too many. It's very few shot learning. Query the API in the back end, and then it comes up with candidates that are close by for further examination. And so it will go and then you can tune how, the confidence levels, what you want to examine, and then go in and look in detail at what it was found. And has found a lot of positive examples of other solar farms. If you find negative examples or examples of locations which weren't marked as positive, you can iteratively add more labels to fine-tune the search. And so through this process of kind of interacting with the backend model, you can quickly get a very high quality data set. We worked with Deepti and Sridhar on understanding our user base more. So we did a survey of our wait list, and we learned a lot about them, including, I think that even though I think we think of like this being something that's available for everyone, that there's still going to be folks with a more technical bent that are going to be interested in using a tool like this. And so we had to think about how to like accelerate their usage, and can assume some familiarity with the concepts, but they don't need to go through all that work. And we explored a lot of like the different use cases which people want to solve with, and one of the have problems to solve with that Earth Index could fit. And one of the biggest opportunities which emerged out of that research, as well as looking at the field as a whole, is certainly in agriculture, which is a big topic. Food is everywhere. It's a third of our global emissions, and there's lots of, I think, really micro niches within the food system, which I think when you have something that someone who has expertise in something very specific can get can get started very easily. I think there's a lot of value in something like Earth Index where they don't need to invest a whole lot of resource up front. Here's a good example. This is a CAFO, or large cattle feeding operation. Cattle operations, by some estimates, account for 14.5% of all global greenhouse gas emissions. It's tremendously large. This is what they look like in parts of the United States, but they look very different in different locations, even within the US, depending on the landscape and the local regulations. Let alone if you look at how these facilities look like in Brazil or China, they have a very different footprint on the landscape. So in order to build what we're trying to build with Climate Trace, which is a global database of all these locations so that they can do emissions modeling by like estimating the number of heads of cattle, and then how manure is managed, and then coming up with methane estimates. it takes a lot of fine tuning in each location to identify these. So Earth Index has proven very effective at this because you can interactively fine tune Earth Index for how things look like in France versus UK versus South Africa. And we've been interactively building up this global data set, which does not exist. There's no other available resource for this kind of global information. We're partway through. This is what was released as of COP in November. So started with kind of like the most prominent places, and we're going to be kind of getting close to like 90% of cattle in the world sometime this year. One more example was a project that we did with Manga Bay, excellent environmental journalism organization. The drug trade has a real impact on the rainforest, and this was looking in Peru in particular. In order to transport cocaine out of the region, narco traffickers will build airstrips in the middle of the Amazon, frequently near to or within indigenous territories or conservation areas. So it's very destructive to the landscape. It's also very dangerous for the local communities. So we're talking about like, transnational organized crime. And these things are very hard to find. Like they have a very distinctive signature, but it's a big rainforest to look through. So we used Earth Index to find something in the order of 75 of these, which were not known before. And that was then utilized by Manga Bay to do on-the-ground reporting and investigations. And they put together a big piece, 67 narco airstrips were found, and we did geospatial analysis to see where they were located. And yes, all the pink are indigenous territories, so these are directly impacting these communities. All right, so final product category is data action. These are decision support tools, assembling data for a particular decision point. And these can be very, very niche. These can be like, you might have like 5 users altogether, but 5 very important users. This is a work that we have been doing for years on groundwater recharge, which is a technique to replenish underground aquifers with rainwater runoff, particularly in California, which has an extremely complicated water system. It's in the news recently. Not everyone understands the complexity of it. But especially with climate change, the amount of rain, as you'll know, is getting much more intense or more dry. And so opportunities to capture that runoff in ways that can support agriculture into the future is really important. So let's see. This is, yeah, that's a kind of a picture of the complication of the water system, of the dams. Each of those colors is a different authority. There's a matrix of canals. It's a very incredibly complicated landscape. Well, image wasn't showing. So there has been a lot of like coalition building and work, to bring people together just around this idea, but it's really been adopted by the water management districts, by farmers, by the state. And this is a picture of the kind of the tool which comes together to like identify which specific field is most eligible, is best positioned to be farmed. Only certain crops can sustain this kind of flooding of the fields. Almonds are one example. There's a lot of almonds in Central Valley. The geology and the water features of the landscape are really important. Proximity to landscape. So this is a tool to like rank and identify where recharge can happen, and then ultimately like you have to set up a relationship with a farmer to go out and literally like open a floodgate. But they get, for them, it's great because they get for the farmers incentivized because they otherwise have to pay for water, but this is a way to get water without, I think they might even have some financial incentive as well. So that's all I have to present, and you're very welcome. Very eager to hear comments or questions.
I think there was
Feel free to reach out.
There was a question from Sridhar and Ruchira, but let's do Ruchira's first, because I think what Sridhar is asking is part of a bigger set of questions we wanted to go over. Ruchira, can you unmute and ask?
Yes. Have you compared your foundation model with, have you compared between different GeoFoundation models on GeoBench or Pangea?
We have wanted to. I would say that we've experimented with a few, but not mainly. We have gotten good results in our application with the GeoLab models out of the University of Munich. We don't develop a foundation model itself. It's within the Earth Index application that we're really looking at, and we're very curious to see how they perform. But quite frankly, we just we've had make choices on where to prioritize, and we haven't had a chance to answer this question of like a benchmarking how different foundation models perform within the application. Something we would really like to do because there's a lot of activity. There are a lot of investments in foundation models right now, and to me, it's we may be missing out on something, but no, we haven't had a chance to do that yet. So far, I guess we've been too happy with what we what we have in hand, but we want to do that very soon within this application of similarity search and change detection.
Great, thank you.
Thank you. All right, please type in your questions or go off mute and ask your question while we're waiting for the questions to come in. Sridhar asked, Sridhar, if you're able to unmute and ask, that would be great too. If not,
yeah, the question is about what is the biggest challenges in scaling geospatial solutions, and related to that is how do you manage costs, especially data costs?
Yes, there's a lot of ways to answer this question. It's a great question. I'll start with the costs, starting with the costs and then going into scaling. We have invested a lot of effort in being very economical with our resources for doing the image processing, which is required to build global composites from Sentinel-2 and other sources, and then generate embeddings and then store them in a database. So much so, we've been very lucky to get donations of credits in various forms. And some of them we're not spending fast enough because we've gotten very efficient at it. So we focus on trying to squeeze as much performance out of that as possible. We can build a global imagery annual composite from Sentinel-2 imagery for on the order of under $1,000. And which is really great because we want to be able to do this on a regular basis. We're aiming for quarterly. And so being able to do that fast and efficiently is important. The other costs are related particularly to running a live database for if we're going to load all those locations for global search into a database, that's going to be a really big database. And so we're thinking about that challenge now to design that in a way that is not going to be a large ongoing cost. But I think that's going to ultimately be our, depending on our usage that we see, it's going to be tricky. We're going to be important to manage. Part of that is, this is not like while we want to scale up, and there's definitely going to be a lot of demand for this. There's certainly a lot of demand for this kind of technology. For what we want to make available as a hosted service, it's really going to be focused on things that align with our mission. And then we need to get into kind of what sort of value proposition, what kind of value exchange is there. Sometimes it's going to just be about supporting a mission. Sometimes it's going to be making sure that what we're doing is sustainable. Sometimes there's going to be more bespoke work where there's maybe more elaborate or more extensive searches that we can be partners in. That's what we're doing with Climate Trace. But even, we haven't totally plotted out the scenarios, but like, it's not going to, it's not Google Maps level used by any means. And there's going to be a lot, it's going to be very spiky. There'll be times when someone's very engaged with it and will need to use that. And other times when, we may not have anyone using it at all. And so how do you manage, you don't want to keep resources up if they're not, not being used, but you also want to have it responsive if someone comes in. And so there's definitely some engineering challenges there that we're looking at. I think the biggest challenge scaling wise, in part, I think we're about to launch global. We've been in alpha for a while, which we're kind of selectively letting people onto the platform. Part of what's limited us is we don't want to bring someone on if their area of interest is not something we've already indexed, and that's kind of takes time for the team to process imagery and make it available. So once we have global, we'll be able to really bring people on much more rapidly. And I think part of the challenge is going to be helping people to figure out if their use case is something that Earth Index is going to be good at or not, because there's a lot of factors from, how distinguishable is it within the landscape? How large is the feature? How frequently do things change? And there's probably some rules of thumb, and there's probably some suggestions that the product could make in order to help people with their searches. But there's also a bit of that's where the learning curve is trying to where we spend time with people now, and we won't want to continue to spend time with people helping them to figure out what's a fit for their use case. But if we're going to scale up, we're not going to be there, holding hands with everybody. So how do we help them get to the point where they can make that assessment of whether this is working for them or not? Because we don't claim that this is the solution to everything. It's certainly not going to, it's not, there's certain problems that it's going to be good at, and certain ones that another approach is better. And we want to be able to communicate that assessment without getting too technical or into the details of things. And that's a challenge right now, thinking about scaling. How do we educate users about what we do and about what other options there might be?
Thank you. Yeah, I mean, in a similar vein too, like these are the challenges associated with it, but like thinking about like trends in geospatial, are there any top 10 trends that you would like to share with the audience?
Sure. I think, I guess I'll answer in a couple ways. One trend that we're very involved with, and which I think has a lot of promise, and we're still trying to figure out how all the ways it is going to be relevant for Earth Index, is the move to cloud native geospatial data. So this is essentially storing data in a way on the internet so that it's easy to work with in applications without requiring someone to download and process that data themselves. And geospatial data can be very big. It can require a lot of special tools to just say there's a huge, here's an example. Say the US has census data. Fingers crossed it still has census data going forward. But you're only interested in information in your county. Getting at that can be quite involved and involve specialist knowledge of like trying to source that specifically. So there are ways of structuring geospatial data sets like that so that it's easy to query, and you don't need to do a lot of data processing. It can just utilize the typical ways that things are queried on the web without the need to set up like an additional infrastructure or APIs. So I think that's and work with very large data sets. So that's pretty exciting trend, which I think will have relevance for us in a number of ways. Another aspect to this, I think is interesting to note is that it gets again to this question I was just talking about, is like educating your and have user base, understanding what things are good for and what they're not. If you, I'm not a full expert in machine learning or in this stuff. I'm not building it myself, but I understand fairly well what's going on, and I frequently have a lot of difficulty if I see something new, some new solution or some new product or tool come on board. We all talk about it in pretty much the same thing. I saw something the other day, which was like, we're take AI models and make that, build infrastructure and make them more accessible for impact. And it's like, wow, we could describe, what is that? Like, what are you actually building? How is it, what is it useful for? How is it distinctive from what we're doing or from something else? And it's, this is not a new challenge in product design and differentiating and helping to educate folks. I mean, look, there's entire like sub-industry, think just like buying a car, the amount you have to educate about. So I don't know if we'll ever get to shortcuts on like, making it, people probably need to invest to understand things, but I think we could, as a geospatial work as a whole, could do a whole lot better at providing frameworks and guidance for end users of these technologies to understand more what the options are without getting into the technical details. I think it's hard challenge, but something we need to do more of.
Oh, I agree. I think education, especially in universities, I mean, I think they have the advantage of students and researchers and professors have the advantage of being in that academic setting and kind of absorbing and learning to process. But if you're in the industry and you're working in geospatial, like setting the time aside to learn about the latest technology is it takes time. Well, thanks everyone for joining. If you liked what you heard today, or if you have feedback on ideas for future topics, please let us know. I've provided the email address and the LinkedIn page here. And, our plan here is to feature experts on various climate technologies every month. So if you follow us on LinkedIn, you can hear about these upcoming events and join us. And a huge thank you to you, Mikel, for the amazing work you've done and for taking the time to share this with us today.
Thanks.
Thank you.
A lot of fun. I was happy to talk with you and everybody else. So yeah, great
Awesome.
time. Thanks.
Thank you.